Dear students, I am Kavita B.S., Assistant Professor, Department of Physics of Government First Aid College, Tiptur. In this session, I will explain the Brownian motion and its features, and also Einstein's explanation for Brownian motion and determination of Avogadro's number. This topic is in the course BSc Physics subject paper 3rd, Thermal Physics, Radiation and Optics 1, and this topic is in the lesson Thermal Physics of Unit 1. Let us start the session. First, we will discuss Brownian motion and its features. Brownian motion was first observed in 1827 by Robert Brown. He is a botanist. And Brownian motion can be defined as the non-stop random and haphazard motion of a particle. It is called as a Brownian motion. And it is perfect, continuous and spontaneous. The features of the Brownian motion are: Brownian motion is a perfect, continuous and spontaneous. And motion of each particle is completely irregular and random. That means no two particles are found to execute same motion. No two particles will not execute the same type of Brownian motion. And it is continuous and it takes forever. Here, the smaller particles appear to be more agitated than the larger ones. And Brownian motion is independent of nature of the suspended particle. And Brownian motion is independent as well as it depends upon the temperature also. Here, Brownian motion is more violent on increasing the temperature. And we cannot modify the Brownian motion by shaking the colloidal solution. And we cannot observe Brownian motion with the particles of larger size. And the last one is we can apply the kinetic theory of gases for Brownian motion also. These are some of the features of Brownian motion. Now we will discuss the Einstein's theory of Brownian motion. Just in this we have the derivation of equation for coefficient of diffusion. That is, Einstein derived the diffusion coefficient in two methods. That is, by considering irregular motion of the suspended particles and also by considering the difference in osmotic pressure caused by the differences in concentration of the suspended particles. First, let us discuss the derivation of expression for diffusion coefficient by considering irregular motion of the suspended particles. For that, let us consider an imaginary cylinder and its axis is along x-axis and its two end faces are P and Q. Here P and Q represents end faces of the cylinder. And these two are separated by a distance S, means the length of the imaginary cylinder is S and its cross-sectional area is A. Then now let us consider or let us assume that N1 and N2 are the molecular concentrations at the end faces of the cylinder. Then the number of particles crossing the surface P to right in unit time, that is along positive x-axis, is equal to of N1 AS, and remaining of N1 AS molecules will travel along negative x-axis or towards left. Similarly, the number of particles crossing the surface Q in opposite direction, that is in negative x-axis or left direction in unit time, is equal to of N2 AS. Then next we will calculate the excess number of particles crossing in the middle layer to right, that is along positive x-axis, should be equal to of N2 AS minus of N2 AS, that is of N1 AS minus of N2 AS. Then here the common term is of and AS, then of N1 minus N2 AS. This represents the excess number of particles crossing in the middle layer to the right direction, that is along positive x-axis. And this is nothing but we can equate this term to d into dn by dx tau a. That is, this is from the definition of diffusion. This term also gives the diffusion phenomena, or that is nothing but number of particles crossing the layer in a time, then that is equal to diffusion phenomena. From the diffusion phenomena, the number of gas molecules is equal to crossing the unit area is equal to crossing the layer is equal to d into dn by dx tau a. Then on equating these two, we get half into n1 minus n2 as is equal to d into dn by dx tau a. Here the term dn by dx represents concentration gradient and also the difference in number of molecules, that is n1 minus n2 should be equal to s into dn by dx, that is number of molecules in an imaginary cylinder. Then by substituting the value of n1 and n2 in this equation, we get of s square is equal to dn by dx is equal to d into dn by dx tau. Then by cancelling this term on either side, we get d is equal to s square divided by 2 into tau. Here the time interval through which gas molecule flows through the imaginary cylinder, and this equation represents the coefficient of diffusion, and this is derived by considering irregular motion of the suspended particles. So next we will discuss the derivation of expression for diffusion coefficient by considering pressure difference. Here also we are considering an imaginary cylinder with its axis along positive x-axis with two end faces separated by a distance s and cross-sectional area is A. And P1 and P2 are the osmotic pressures at the two ends P and Q respectively. Then from the gas equation, that is the gas is flowing through the cylinder in that condition. Here by using gas laws equation, we have P1 is equal to N1 kT and P2 is equal to N2 kT. That is pressure at the two ends of the imaginary cylinder, that is at P and Q. Then due to this pressure, the cylinder experiences a force and it is equal to P1 minus P2 into A. Then that is equal to N1 minus N2 kT. Then this force is along positive x direction. So this force is the force experienced by total number of molecules within the cylinder. Then now we will calculate the force experienced by a single particle within the cylinder. Then that is given by F dash is equal to N1 minus N2 kTA divided by NAS. Here NAS represents total number of gas molecule within the cylinder. Then the force is multiplied by total number, we get force experienced by a single particle, and that is equal to N1 minus N2 kTA divided by NAS. And also we have N1 minus N2 is equal to S into dN by dx. Then on substituting this value in the above equation, we get F dash is equal to dN by dx into kT divided by N. Here this is nothing but viscous force. Viscous force experienced by the gas molecule, and from the Stokes law we have one more equation for viscous force, that is equal to F dash is equal to 6 pi eta AB. Then on equating those two equations, we get kT by N dN by dx is equal to 6 pi eta AB. This is from Stokes equation. Then here we can write, that is for N into V term. Here NV represents the number of particles moving to right, that is along positive x-axis, per unit area in 1 second, that is equal to kT divided by 6 pi eta a into dN by dx. Then this is nothing but, again from the definition of diffusion, we have NV is equal to d into dN by dx. Number of particles moving per unit area in unit time is equal to d into dN by dx. Then on equating those two equations, we get d into dN by dx is equal to kT divided by 6 pi eta a into dN by dx. Here d is equal to kT divided by 6 pi eta a. Since k is Boltzmann constant, here is a small letter k, that is Boltzmann constant. Then ratio of gas constant, universal gas constant, Avogadro's number. Then on substituting k value, then we get d is equal to RT divided by Na into 1 divided by 6 pi eta a. So this equation represents the coefficient of diffusion by considering difference in osmotic pressure, which is caused by the differences in concentration of the suspended particles. And this equation we have derived, that is by considering irregular motion of the suspended particles. So from these two we can derive or we can calculate Avogadro's number by equating these two equations. That is RT by Na into 1 divided by 6 pi eta a is equal to S square divided by 2 tau. Then here Na is equal to, on rearranging the terms, we get Na is equal to RT tau divided by 3 pi eta a S square. So by knowing these terms, we can calculate the Avogadro's number. So this is about Brownian motion and Einstein's explanation for Brownian motion and the determination of Avogadro's number. Textbooks for your reference. Thank you.